Welcome! In this session, we'll dive into the LeetCode problem number 875, Koko eating bananas. This problem challenges us to optimize a solution that ensures Koko can finish her bananas within a given time frame. We'll explore different approaches, analyze their efficiencies, and discuss how to approach similar optimization problems. Let's get started. Koko loves eating bananas, and the problem revolves around her trying to finish all the bananas in a given set of piles. Each pile has a specific number of bananas, represented by the array piles, where the ith element corresponds to the number of bananas in the ith pile. She has h hours before the guards return and can set her eating speed, k, which is the number of bananas she eats per hour. If a pile has fewer than k bananas, she simply eats all the bananas in that pile and moves on to the next pile in the following hour. Importantly, Koko can only eat from one pile per hour, and the goal here is to determine the smallest possible value of k that allows her to finish all the bananas within the given h hours. The problem specifies the input format where piles is a list of integers and h is a positive integer, as well as the output, which is the minimum integer k that satisfies the constraints. To understand the problem better, let's look at an example. Suppose piles is 3, 6, 7, 11, and h is 8. In this case, the minimum speed k that allows Koko to finish all the bananas within 8 hours is 4. Here's how it works. In the first hour, Koko eats all 3 bananas from the first pile, leaving it empty. In the second hour, she eats 4 bananas from the second pile, leaving 2 bananas in that pile. In the third hour, she finishes the remaining 2 bananas from the second pile. In the fourth hour, she eats 4 bananas from the third pile, leaving 3 bananas there. In the fifth hour, she finishes the remaining 3 bananas from the third pile. In the sixth hour, she eats 4 bananas from the fourth pile, leaving 7 bananas there. Finally, in the seventh and eighth hours, she finishes the remaining 7 bananas from the fourth pile. By the end of the 8 hours, all piles are empty, and we see that k equals 4 is the minimum eating speed required. Now let's consider another example. Here, piles is 30, 11, 23, 4, 20, and h is 5. The minimum speed k in this case is 30. Let's see why. In the first hour, Koko eats all 30 bananas from the first pile. In the second hour, she eats 30 bananas from the second pile, which empties it since it only had 11 bananas. In the third hour, she eats 30 bananas from the third pile, leaving it empty as well. In the fourth hour, she eats 30 bananas from the fourth pile, which also empties that pile. Finally, in the fifth hour, she eats 30 bananas from the fifth pile, clearing it too. By eating at a speed of k equals 30, Koko ensures that all piles are empty within the 5-hour limit. Therefore, k equals 30 is the minimum speed required for this case. In another scenario, let's take piles equals 30, 11, 23, 4, 20, and h equals 6. Here, the minimum speed k that allows Koko to finish within 6 hours is 23. Let's break this down. In the first hour, Koko eats 23 bananas from the first pile, leaving 7 bananas there. In the second hour, she finishes the remaining 7 bananas from the first pile. In the third hour, she eats 23 bananas from the second pile, leaving 11 bananas there. In the fourth hour, she finishes the remaining 11 bananas from the second pile. In the fifth hour, she eats all 23 bananas from the third pile, leaving it empty. Finally, in the sixth hour, she eats all 23 bananas from the fourth pile, clearing it as well. By the end of the sixth hour, all piles are empty, and we find that k equals 23 is the smallest speed that works. The constraints and edge cases provide additional insights into solving this problem. The constraints specify that the number of piles can go up to 10,000, and each pile can contain up to 1 billion bananas. Additionally, the time h can be as large as 1 billion hours. These constraints highlight the need for an efficient solution. For edge cases, consider situations like a single pile where k must be at least the ceiling of the pile size divided by h. If h is very large, Koko can eat at a leisurely speed of k equals 1 since she has plenty of time. On the other hand, if h is equal to the number of piles, Koko must eat at a rate equal to the size of the largest pile to finish 1 pile per hour. Lastly, if all piles have only 1 banana, then k equals 1 is always sufficient. These examples and constraints set the stage for designing an optimal approach to solve the problem. To solve the problem of Koko eating bananas, we can explore a range of approaches, starting with the brute force method. In this approach, we iterate through all possible eating speeds, from 1 up to the size of the largest pile of bananas. For each speed, we calculate the total number of hours it would take to eat all the piles, rounding up for any partial piles, and check if it meets the required condition of finishing within the given hours. While this method is simple to implement and easy to understand, it has significant drawbacks in terms of efficiency. The time complexity grows with both the number of piles and the size of the largest pile, making it impractical for large inputs. For example, if the largest pile contains millions or even billions of bananas, iterating through all possible speeds would take an enormous amount of time. A more efficient strategy leverages binary search to find the minimum valid eating speed. Here, instead of testing each speed sequentially, we treat the range of possible speeds as a sorted array and search for the optimal speed. The key insight is that the total hours required to finish eating is a monotonic function of the eating speed. When the speed increases, the hours decrease. This property allows us to use binary search effectively. We start with the range from 1 to the size of the largest pile and calculate the midpoint. For each midpoint speed, we determine whether it satisfies the condition of finishing within the given hours. If it does, we narrow the range to search for smaller valid speeds, otherwise, we adjust to search for larger speeds. This approach drastically reduces the number of speeds we need to evaluate, resulting in a time complexity of n*log max pile, where n is the number of piles. This makes it far more scalable than the brute force method, especially for larger inputs. Given the advantages in efficiency and scalability, the binary search approach is the clear choice for solving this problem. While the brute force method is simpler to implement, its inefficiency for large constraints makes it impractical. Binary search, on the other hand, effectively narrows down the search space, taking full advantage of the monotonic relationship between speed and hours. Recognizing this monotonicity was a pivotal moment in our approach, as it reframed the problem from an exhaustive search to a more targeted one. Although binary search requires slightly more effort to implement, its performance gains far outweigh this trade-off, especially for larger datasets. Ultimately, the binary search approach strikes an excellent balance between clarity and computational efficiency, making it the ideal solution for finding Koko's minimum eating speed. To understand this problem, imagine Koko has a number of banana piles, and she needs to eat all of them within a given number of hours, h. The catch is, she can decide how fast she eats each hour, represented by the speed k, which is the number of bananas she eats per hour. If a pile has fewer bananas than k, she finishes the pile in less than an hour and moves on to the next. Our objective is to determine the minimum value of k that allows her to eat all the bananas within the allotted time. To solve this, we start by defining the range of k. The slowest possible speed is 1 banana per hour, and the fastest is the size of the largest pile, max piles, since eating faster than the largest pile in 1 hour doesn't make sense. This forms our search space, 1 max piles. The next step involves determining if a specific speed k is feasible. Using a helper function, we calculate the total hours required for Koko to eat all the piles at speed k. For each pile, the time required is given by the formula ceil piles I/k, which can be computed efficiently using integer math as piles I plus k1 //k. If the total hours are within h, the speed is considered feasible. This sets up the foundation for our binary search approach to find the optimal speed k. Now that we've defined our search space and the feasibility check, we can implement the binary search to find the minimum k. We start with low set to 1 and high set to max piles. In each iteration, we calculate the middle value mid is low plus high //2 and check if mid is a feasible speed using the helper function can_eat_all mid. If it is feasible, mid might be our answer, but we need to check if there's a smaller feasible speed, so we update high to mid 1. If it's not feasible, we know the speed must be higher, so we update low to mid plus 1. The binary search continues until low exceeds high, at which point the value of low gives us the minimum speed that satisfies the condition. This approach is highly efficient. Instead of testing every possible value of k linearly, the range of potential speeds is halved in each iteration, resulting in a logarithmic reduction. The helper function ensures we only evaluate valid speeds by summing the time required for each pile, and edge cases like when h equals the number of piles or when h is very large are handled seamlessly. This combination of binary search and the feasibility function ensures both accuracy and efficiency. Let's discuss the data structures and complexity involved in this algorithm. First, the input array pile stores the number of bananas in each pile. As we iterate over it to calculate total hours for a given speed k, its role is critical in determining feasibility. The variables low, high, and mid are the core components of the binary search, helping us efficiently narrow the range of possible speeds. The helper function encapsulates the feasibility check, making the code modular and easier to debug. In terms of complexity, the binary search runs in O, log, max, piles, iterations, as the search space is halved in each step. For every k tested, we calculate the total hours by iterating over all piles, which takes O, n, time where n is the number of piles. Therefore, the total time complexity is O, n asterisk log, max, piles, combining the iterations of the binary search with the per iteration cost. The space complexity is O, 1, as we only use a few variables and no additional data structures. Here's the pseudocode for this solution, where we define the helper function can_eat_all, initialize the binary search variables, and iteratively narrow the range of k based on feasibility checks. In the pseudocode, the binary search continues with the feasibility check determining whether to adjust low or high. If mid is a feasible speed, high is reduced to mid 1 to search for potentially smaller speeds. Otherwise, low is increased to mid +1 to find a feasible speed. The algorithm eventually exits the loop when low exceeds high, and low holds the minimum speed k. To solidify this, let's walk through an example with piles equals 3, 6, 7, 11, and h equals 8. Initially, low is set to 1 and high to 11, the size of the largest pile. In the first iteration, mid is calculated as 6. Checking can_eat_all, 6, we compute the time for each pile as seal, 3/6, seal, 6/6, seal, 7/6, and seal, 11/6, which sums up to 6 hours. Since this is within the limit of 8 hours, 6 is feasible, and we update high to 5. In the second iteration, mid becomes 3. The time for each pile at this speed is 10 hours, which is not feasible, so we increase low to 4. This process continues as the binary search narrows down the range. In the third iteration of our example, mid is calculated as 4. Checking can_eat_all, 4, we compute the time for each pile as seal, 3/4, seal, 6/4, seal, 7/4, and seal, 11/4, which sums up to exactly 8 hours. Since this is feasible, we update high to 3. At this point, low becomes greater than high, and the loop exits. The value of low, which is 4, represents the minimum eating speed k that allows Koko to finish all the bananas within 8 hours. Thus, the final answer for this example is 4. This demonstrates how binary search efficiently narrows down the possible speeds, leveraging the feasibility function to ensure correctness. By combining mathematical insight, efficient search techniques, and careful handling of edge cases, we've solved the problem in an optimal way. The solution to the Koko eating bananas problem uses a binary search approach to determine the minimum eating speed, k, that allows Koko to eat all bananas within h hours. The first step is defining the helper function hours_needed, speed, which calculates the total hours required for Koko to finish all the piles at a given eating speed. Using ceiling division, pile plus speed 1///speed, ensures that partial piles are rounded up correctly. Next, the binary search is set up over the range of possible speeds, where the lower bound, left, is 1, minimum speed, and the upper bound, right, is the largest pile in piles, maximum speed Koko might need. The goal is to narrow down the range to the smallest k that satisfies hours_needed, k equals h. In the binary search loop, mid represents the candidate speed. If hours_needed, mid, is less than or equal to h, it means Koko can eat all bananas in time at that speed, so the search continues in the left half by setting right equals mid. Otherwise, the speed is too slow, and the search moves to the right half with left equals mid +1. The loop continues until left equals right, at which point the minimum eating speed is found. The function then returns left as the result. This approach is efficient, with a time complexity of O, n asterisk log, max, piles, where n is the number of piles, and log, max, piles, is the number of iterations in the binary search. It ensures that the solution is both optimal and scalable for large inputs. Here, we begin by creating a solution class and defining the method min eating speed. This method takes in an array of integers, piles, which represents the number of bananas in each pile, and an integer h, which is the maximum number of hours Koko has to finish eating. To calculate the number of hours needed for a given eating speed, we define a helper function as a lambda expression. This function takes an integer speed and calculates the total hours required by iterating over each pile. For each pile, we use ceiling division to determine how many hours it would take to eat that pile at the given speed. The result is accumulated in the total hours variable. Next, we set up a binary search to find the minimum eating speed. The left boundary, left, starts at 1, which is the slowest possible eating speed, and the right boundary, right, is the maximum value in the piles array, as that represents the largest pile Koko might need to eat in 1 hour if there's just 1 hour available. Within the binary search loop, we calculate the midpoint, mid, between left and right to test it as a potential eating speed. If the hours needed at this speed, determined by the hours needed function, is less than or equal to h, it means Koko can finish eating within the given time. In this case, we update right to mid to see if a slower speed might still work. Otherwise, if the hours needed exceed h, we know the speed is too slow, so we move the left boundary up to mid plus 1. Once the loop exits, left will hold the smallest possible eating speed that allows Koko to finish eating within h hours, and we return this value. To solve this problem, we need to determine the minimum speed, denoted as k, at which Koko can eat all the bananas in no more than h hours. In this example, the piles of bananas are 3, 6, 7, 11, and Koko has 8 hours to finish them. To start, we use binary search to efficiently find the solution. We initialize our search range with left set to 1, the smallest possible eating speed, and right set to 11, the size of the largest pile. Now, for the first iteration, we calculate the midpoint of the range, mid equals 1 plus 11, // 2 equals 6, and use this as Koko's hypothetical eating speed. By simulating this speed, we calculate the total time required. Eating pile 3 takes 1 hour, pile 6 takes 1 hour, pile 7 takes 2 hours, and pile 11 takes 2 hours, leading to a total of 6 hours. Since 6 is less than or equal to h, this means speed 6 is feasible, so we narrow our search range by updating right to 6, making it our new upper bound. Next, we perform the second iteration of binary search. With the updated range, we calculate mid equals 1 plus 6, // 2 equals 3 and use this as the eating speed. At this speed, we compute the total hours required. Eating pile 3 takes 1 hour, pile 6 takes 2 hours, pile 7 takes 3 hours, and pile 11 takes 4 hours, resulting in a total of 10 hours. This exceeds the allowed 8 hours, so speed 3 is too slow. To adjust, we update left to mid plus 1, which is 4, making it our new lower bound. For the third iteration, we calculate mid equals 4 plus 6, // 2 equals 5 and test this as the speed. At speed 5, eating pile 3 takes 1 hour, pile 6 takes 2 hours, pile 7 takes 2 hours, and pile 11 takes 3 hours, summing to exactly 8 hours. Since 8 is within the allowed time, speed 5 is feasible, so we update right to 5, further narrowing the range. Now, for the fourth iteration, we calculate mid equals 4 plus 5, // 2 equals 4 and test this as the speed. At speed 4, eating pile 3 takes 1 hour, pile 6 takes 2 hours, pile 7 takes 2 hours, and pile 11 takes 3 hours, again totaling 8 hours. Since this is within the allowed time, speed 4 is feasible, so we update right to 4. At this point, left and right both equal 4, which means the binary search has converged. The minimum eating speed that allows Koko to finish all the bananas within 8 hours is k equals 4. In the second example, we apply the same binary search approach to a new set of piles, 30, 11, 23, 4, 20, with only 5 hours available. We initialize the search range with left set to 1 and right set to 30, the size of the largest pile. For the first iteration, we calculate mid equals 1 plus 30, // 2 equals 15 and test this as the speed. At speed 15, eating pile 30 takes 2 hours, pile 11 takes 1 hour, pile 23 takes 2 hours, pile 4 takes 1 hour, and pile 20 takes 2 hours, resulting in a total of 8 hours. Since 8 exceeds the allowed 5 hours, speed 15 is too slow, so we update left to mid plus 1, which is 16. For the second iteration, we calculate mid equals 16 plus 30, // 2 equals 23 and test this as the speed. At this point, the total hours required is calculated to be 7, which is again greater than the allowed 5 hours. The binary search continues, repeatedly narrowing the range by adjusting left and right until the two converge. Ultimately, the minimum eating speed that allows Koko to finish all the bananas within 5 hours is found to be k equals 30. To analyze the time complexity of our solution, we need to consider two key components. First, the binary search process, which determines the optimal eating speed. The range of possible speeds extends from 1 to the maximum pile size, and binary search systematically halves this range at each step. This gives us a time complexity of O log max piles for the binary search. Second, at each step of the binary search, we call the hours_needed function to compute the total hours required for a given eating speed. This function iterates through all the piles, so its complexity is O, n, where n is the number of piles. When we combine these two components, the total time complexity becomes O, n asterisk log, max, piles, with the binary search contributing the log factor and the hours calculation adding the linear factor at each step. Now, let's examine the space complexity of the solution. It's O1, because the algorithm does not use any additional data structures. We only keep a handful of variables, like left, right, mid, and total_hours, to perform the calculations, and these take up constant memory regardless of the input size. The input list piles is used directly without creating copies or requiring extra storage. Additionally, we can break down the best, average, and worst cases for this algorithm. The best case happens when the binary search quickly identifies the correct eating speed within the first few iterations, but in terms of big O, this doesn't change the overall complexity, it still remains O, n asterisk log, max, piles. In both the average and worst cases, we perform the full binary search across the entire range from 1 to max, piles, which again results in O, n asterisk log, max, piles. Let's compare this approach to a brute force method. A brute force solution would involve testing every possible eating speed from 1 to max, piles, and calculating the total hours required for each. This would take O, max, piles, asterisk n, time because we would iterate through all n piles for each speed in the range. By contrast, our binary search approach is much more efficient. Instead of testing every single speed, binary search narrows the range to only O, log, max, piles, speeds, and for each of these, we calculate the hours in O, n, time. This brings the total complexity down to O, n asterisk log, max, piles. To break that down mathematically, if we let m represent the maximum pile size and in the number of piles, the binary search takes O, log m iterations, with each iteration requiring O, n, time to compute the hours. Combining these, the total complexity is O, n asterisk log m, which is far more efficient than the brute force method and dominates the runtime of the algorithm. When solving this problem, there are a few common mistakes to watch out for. First, failing to handle edge cases in input sizes can lead to incorrect results. For instance, if there's only one pile or if the number of hours is extremely large or small, your implementation might break. Consider the example where piles equals 1000 and h equals 1000. The correct answer is 1, as Koko can eat the entire pile in 1 hour each day. However, poor boundary handling could cause miscalculations. Next, a naive approach might involve a linear search through all possible eating speeds, but this is highly inefficient with a time complexity of O, max, piles, asterisk n. Instead, binary search drastically reduces this to O, n asterisk log, max, piles. Another common issue arises when calculating total hours for a given speed. If you mishandle the ceiling operation or round down incorrectly, your results will be off. A reliable method is to use integer math, such as pile plus speed 1 / speed, to avoid floating point inaccuracies. Lastly, setting the binary search range incorrectly is a frequent pitfall. The lower bound should always be 1, representing the minimum speed, and the upper bound should be the largest pile size, as Koko could theoretically eat it in 1 hour. Overlooking these boundaries can lead to infinite loops or wrong answers. Another mistake to avoid is not breaking ties correctly. When multiple speeds satisfy the given condition, your implementation must return the smallest valid speed. This is essential for ensuring correctness. Now, let's focus on some interview insights. This problem is a great example of applying binary search on the answer space. Instead of searching for a value within the input, you're narrowing down the range of possible answers, which is a common technique in binary search problems. It's also important to highlight the efficiency of binary search compared to brute force. You should be prepared to explain why binary search is optimal and how you calculate the total hours needed for a given speed. Clear communication is key. Make sure you can articulate the role of the helper function that computes total hours and how it integrates into the binary search process. Finally, interviewers may introduce variations, such as adding constraints like a maximum number of bananas Koko can eat per day or changing the objective to minimize total hours instead of speed. Be ready to adapt your solution to these potential follow-ups. This problem shares similarities with other classic binary search problems. For instance, LeetCode 1011, capacity to ship packages within D days, also involves binary search on the answer space to determine the minimum capacity required. Another example is LeetCode 410, split array largest sum, which requires dividing an array and using binary search to minimize the maximum sum of subarrays. LeetCode 774, minimize max distance to gas station, is a variation that applies binary search to decimal values to minimize the maximum distance. Lastly, LeetCode 1482, minimum number of days to make M bouquets, employs binary search to determine the minimum number of days required under specific constraints. While brute force approaches might seem straightforward, they're impractical for large inputs due to inefficiency. Binary search, with its O and asterisk log, max, piles, time complexity, strikes the right balance between performance and correctness. Although greedy heuristics, like always eating the largest pile first, might seem tempting, they often fail to meet the time constraints. Mastering binary search techniques here will not only solve this problem efficiently but also equip you with skills to handle a wide range of similar challenges. Thank you for joining this session on solving Koko eating bananas. We used binary search to optimize Koko's eating speed within the given constraints. This approach is efficient and versatile for similar problems. If you enjoyed this explanation, be sure to like, subscribe, and stay tuned for more problem-solving insights. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!